Morning, June 16th, 2017. This is video number 15. Didn't make a video yesterday. Okay, I'm going to explain as briefly as I can how everything that exists would have mass. Okay, first of all, I'm just going to show a picture in my book. Those are starting out with hydrogen and helium and helium-3, helium-3 before helium-4, and then you got lithium, beryllium, boron, nitrogen, oxygen. And this is how I believe nuclei configure in a specific way, that there are wedge protons, and they wedge between neutrons. The neutrons actually have higher charge, and their surface particles are more repelling. Because their interior has a higher charged photon in the center, it takes more uncharged photons to neutralize it, cover it, and then the presence of those uncharged photons means over the top of them you need more mid positives that finish them off so they quit adding mass. Anyway, that's the way the system works. The center particle, the way that a neutron behaves indicates that, because they are involved in radioactivity a lot. And I think it's because usually it's because some of them, there are too many of them on a nucleus, and they're loose. If they don't have wedge protons between them, holding them apart, they will clap. And I think that's what you see in tritium. And when they do, then you got beta particles start coming off of them, and beta, in radioactivity you have alpha is a form of radioactivity output, and then you also have beta is very common. And beta electrons actually attach to the surfaces of nucleons. They don't just orbit. And so that's a start. Here, one thing I want to show you, and this is kind of where I finished up with the particle system. You may not be able to see, but there's my system has an electric particle that is involved in electricity. Those are actually two photons, a yellow green and a yellow. Now those are also involved in visible light. I'm going to explain that a little bit here, but the next one is an R3, then you got an R15, and these are the shell. They make shells out from nuclei, and they completely encase. There are so many of these they can make spherical shells, these radio particles, and they all have their specific, they're all specific, and their mass and their design. Anyway, I've had 5 of these, not counting the electric, and I ended up with 6. I believe there are 6 of those, and so there'd be 6 individual shells. The electric particles have the least mass, and they're individuals and individual photons, and they can beat anytime you have a deficit created by movement, disturbance. Electric photons can beat the other radio particles to a spot over a nucleus, and so that's why electric current is possible, I believe. But anyway, I won't go into that. There are 4 electrons proper. And when I talk about electrons proper, I'm talking about mainly beta particles. Now I've got 2 of those. One has a mass of 27 photons, the other one 43. So there's a beta 27 and a beta 43. And that's, I believe, and they make 2 separate shells. And what makes electrons and radio particles hover at a certain distance is their mass and how many repelling photons are on their surfaces. If they're larger, they need more repelling photons on their surfaces in order for them to stop adding mass. And then those repelling surfaces mean that they have more repel to what is ultimately a repelling surface of a nucleus um, on the surface. There has to be repel there for it to work like it does. Anyway, all of these congregate a certain distance away from nucleus in relation to one another and in relation to the nucleus. And actually, in my system, if you saw this last one, it would be a positron. There would be a positron shell. There's not nearly as many positrons in the environment as there are beta electrons. There are not nearly as many beta electrons as there are what I call neutrino electrons. And there are not nearly as any of those as there are all of the radio types. The radio types make spherical shells. Now I've already explained how they can spawn an orbiting shell beyond their spherical shell. Particularly, I think that it would only happen with the outermost shell of the radio particles. Anyway, this is where things stand. This page has the math for all of this, where I finally arrived with it. It's hard. This is much bigger on my website. These pages are much bigger on my website and easier to read. This goes with that. Tells how many of each kind of radio particle are in each shell, and how that is determined. When I did this page, when did I do this? This was on April 14th of 2014. When I did this, I didn't have it quite right. When I got to sulfur, I had to change. Now you can find this all on my website, but it wasn't balancing out. It wasn't being harmonious. It wasn't working out. I could see, and I had too few, and so it's actually been changed. There's the number of the number of R3 units. That's my innermost radio shell. It has particles of a mass of 3, and there was 80 when I did this. 80 per nucleon. 80 per nucleon. I think it is. I have to read this again, but and then. Anyway, it had to be bumped up. It ends up being around 100, I believe it is, but I'd have to go back and check. But I want to show, okay, I have to skip more to the back to find this part. Okay, this page starts to get back into that again. This is how these particles are charged and made, these individual photons. In a collection. This shows the collection. There are layers in the collection. The more innermost particles get charged more. They're distorted more to being more cube-shaped. They burst out into space because of that. They're naturally spherical, and then being compressed into more cube-shaped. They're trying to flex back to become. They don't want to become cubes. And anyway, so they burst out into space in two opposite directions. The Milky Way is only on one side of this. There's a symmetrical arrangement of galaxies on both sides of this collection in space. It recycles. Everything recycles. This page, this is really the page I wanted to show the most. And this was done. I'm not seeing the date on this one, but this was done before that first page I showed in this video by quite a bit, probably 4, 5, 6 months. But here's a nucleus. It's not to scale. It's just a beryllium, I think it is. Or no, is that nitrogen? It's beryllium. Anyway, nucleus, and then here are the electric particle, the electric photons that occupy spaces immediately, if they don't have extras like a buildup of electric charge current, then they occupy the the area next to the nucleus. Then you have the R3s. Then the next one is, let's see, I'd have to go look, but finally you get out to this outermost. Now this only has 1, 2, 3, 4, 5. So this was early on. This is before I had 6 radio shells. And but this is interesting here because I usually refer to this is the first of the electron. There's not enough of these to make a spherical shell, and this is probably what really exists. It's a neutrino electron, and it makes a shell just outside of the outermost radio shell. And the radio shells are completely spherical. They don't orbit because they're filled, and you can see them when you look through cotton fabric at direct sunlight. You can see there's a gray area it's large, and it's occupied by all of these, and it's spherical. That's why it's gray, and it looks like, you know, a dot, you know, a pretty big, good sized gray dot, but it's actually shell over shell over shell over shell. And then, but the electrons are out from that, and they make black circles, black lines that are circles. This is the next one. There are not as many of these. That's why they make, and that's why they orbit. That's why they make a planar shell. And they orbit in whatever direction, just have the radiation happens to move, whatever direction they can move. They'll either go one direction or the other. The next one out is the beta 27. Yeah. And then the beta 43 makes another shell. And these are what I actually saw in 2011, and the big atoms that attach to cotton fibers. The cotton fibers are mostly made of carbon. Carbon's a very small atom. You don't see it. You can see water molecules in it when you wet the fabric. But anyway, the outermost is the shell, is the positron. In my system, see, the positron has a mass of around 67 photons, and the neutrino electron has a mass of 15. Now, I've kind of gone back and forth, thought that the neutrino electron had a mass of 7, and I had and they were all yellow now, but you'll find in my book where I draw it that way sometimes, but I think I've abandoned that. It's more spherical. If it has 15, it's more spherical. Okay. There's a reason why the 7p7 mass infrared particle, which collides into everything. That's why you can measure temperature by it. It collides into everything, and it'll always indicate the velocity or temperature of whatever it's colliding into, because it doesn't orbit because it's not attracted enough. But they're ubiquitous with everything else in the environment. But there's more photons in the environment than anything. These are in space. These are next to a gravity source. They're everywhere. Now, there are different concentrations, but anyway, as far as diameter is concerned, the R3 is, okay, a photon is, I've mentioned this before in these videos. There's a photon on this page right there, and it's 13 pixels on the I use paint.net as a software to work on these, and it's 13 pixels in that system. And then from, all you have to do is find your base unit, your digit, and then add everything up from there. And then the R3 is 39 pixels in diameter. The R4 is the next one out. It's 37 pixels in diameter. Now, it's smaller than the R3. They're just stacked. There's two repelling particles on both sides. They're actually the yellow-orange in my system, so they're kind of like a gamma particle, but so they're highly repelling, and you have to have something that's of low charge in the middle between them, keeping them separated, that they're attached to. But anyway, The R5 is another radio particle. It has 39 pixels. R6 has 39 pixels. The R7 has 39 pixels of diameter. The neutrino electron 7 would have 39, but I'm starting to doubt that's even exists. That neither the 7 particle neutrino electron or the 7 mass infrared particle, there's reasons why those wouldn't actually exist. They wouldn't work. Anyway, the NE15 is next. It's got 41, and that's the one with 15, a mass of 15. You got the beta 27, is 51 pixels of diameter. The beta 43 is 54 pixels of diameter. The positron is 54 pixels, and then the positron is 64 pixels of diameter. Now, in my system, here's more of that. Here's another picture of, this is what's actually going to be a nucleon. And they would have some electrons and other stuff attached in these little where there's bumpy spots that make valleys. All that stuff gets filled up. That's why there's radioactivity. It's because that's depending on what's there. And then, but anyway, here's a picture of a positron, beta 43, beta 27. There's my neutrino electron, which that's the let's see here. Yeah, that's the one that has yellows covering its black, and that was the first electron I ever came up with when I wrote Endless Cycle Universe. But when you really think it through and develop this enough, that one kind of goes out the window. This is a nucleon, and those are all positrons. Those red circles connected. Now that's you can really make a nice sphere with 15 smaller spheres. But you got valleys there in between them, but they'll make nice spheres. I believe that's a nucleon. And it'll have other stuff filling those little the bumps in between the bumps. So it's much nicer in reality than that. But that's what's inside. And as far as what J.J. Thomson came up with, 1836 of a proton is an electron, the mass of an electron. I believe that's the photon. He was actually, when he was doing cathode rays, trying to measure mass, he came up with 1836 of a, I said earlier in a video that it was 1832nd, it's 1836. Anyway, that would be the mass of a photon. And that's the way I've done this, used that number. And would be the mass of cathode ray emissions. The particles that are coming out of cathode rays are photons. And but anyway, as far as what I'll mention about a collider here now, like at CERN, when they're okay, let's just say that a proton has 15 and a neutron has 15 positrons in it, okay, that are connected. And when they're basically two protons that have 15 of these in each, when they collide in a super collider, they come apart. If they collide with the right amount of thrust, which is caused by electron volts, with the correct amount of electron volts is pushing these toward one another. When they break apart, they would, if I'm right, you should see 30 spheres come out, pretty good sized spheres, and they would be, because these are attached, and they could collide so that they release from one another, and you should be able to see them. Now, the reason you see these is because with the camera equipment is basically made to be like the retina of a human eye, in that it's sensitive to photons. It's not sensitive to radio particles. it evolved to be sensitive to photons, and it ignores radio particles. Radio particles are hitting your eye, but you don't sense them, you don't see them because the equipment to sense them isn't there. It our eyes pick up visible light, and so do the cameras designed to photograph these collisions in a super collider. And when these collide, there another thing I'll show here is that there is amidst all of these particles that are surrounding atoms, and even in between their shells, as all this is orbiting, all that orbiting and whatever is going on, you've got just a enormous, a number of photons and electrons and infrared particle, more radio particle. It's just a soup of that stuff in there. And the reason that light can get through all of that is because they generally, like white light anyway, makes a packet where the photons in visible light are attracted enough that they arrange in a line that's following one another, because there's some of them that are a little bit attracted, and that makes them line up. Well, attrition, two things causes light to make it as far as it through all that soup. First of all, the leading ones are lost by attrition. They collide and they don't have. But when some of those that are first developing when a group of light particles or photons are sent out from a source, is when they're arranging, you're going to have some attrition that they're just going to be knocked back in the environment. But the ones behind them the ones ahead have made a way for the ones behind, and that's going on all the time. But more importantly is the charge. The ones that will become the leaders of these packets when it's white light, for example, they are the yellow will become the leader, because they have enough repel to push their way on, to move things over as they're flying through at the great velocity they do fly through. These repelling surfaces, the repelling surfaces of radio wave particles, but in this case, just of the single photons itself, that repel that they have prevents them from colliding, and they can just keep going and going and going. That's how you have this soup out there. You don't have actually have emptiness, and that's why it can work. I was going to show, let's see, on the page where my particle system is. Let's see here. You have this is depicted. Oh, here it is. Okay, now, this is all kind of small in the book, but it's big on my website. Now, on this side, you've got some molecules that I've drawn, and some of those can be improved on. Nitrogen I had to change, but I didn't change it on this page. But over here, you probably can't see it, but there's that soup of subatomic particles in between atoms, in between their shells, out in space, restocking the sun, whatever. Those are everywhere, and I've got little dots all over the place on this side of the page with those molecules. And so, let's see, is there anything else I want to add to this? Yeah, what I was trying to get around to saying was that in a super collider, okay, they don't adjust the electron volts so that just the positrons break apart. I think I've actually seen that before, but can't find it anymore. But what you see is like when they made caused a collision, like what made what they term the Higgs boson. Well, there's lots and lots of photos like that that are made by cameras and super colliders. Anyway, I want to explain what you're actually seeing there with my system, and that's where all of it that you've heard. I was going here. I wanted to say this for my system, and for everything that exists having mass. Okay, you think that doesn't work, that you need to have all this empty space between everything. Okay, well, it does work. It all works. When there's a, oh, by the way, when you have radio waves and magnetic fields and everything, speeding particles in opposite directions around a loop that's however many miles long, like at CERN, and then the protons end up colliding, and you photograph that, which is usually okay, and you're almost at the speed of light. This side has almost reached the speed of light. This side has almost reached the speed of light, and then they collide. They're actually colliding at near double the speed of light. Okay, there is no reason to say that nothing can travel faster than the speed of light. That's like religious dogma. Okay, these are going so fast, and the speed of light, you can exceed the speed of light, and you will get something visible, because all you have to do is, in that thick soup of what's mainly made up of photons, individual single photons of visible light. Those are the low middle charge and just below middle charge, that they have their own repel, and that's why there's so many of them as singles, because they're just everywhere among everything else that's just everywhere. And there's different concentrations of this soup, in space or near a gravity source. It would be more concentrated than it is, out away from a star, out away from a planet, just out in space. But there's a lot of it out there too. But anyway, the thing is, when these collisions happen and they're way over the speed of light, these things are breaking apart and recoiling out at more than the speed of light. And when you've got that kind of, if you have the right kind of particles being collided into, and then they move at the speed of light, now they have enough energy so that cameras that are made somewhat similar to our retinas can pick those up as being visible. That's what we're seeing in a super collider. And when you see these little individuals, you say, oh, that's a photon. So, and then it's emitting like from in its interior, it's just magically emitting light, okay, massless light or whatever. No, it isn't. What you're seeing probably are 15 particle neutrino electrons and stuff like that that's spherical, okay? And as that stuff is part of those two protons that are broken, the positrons in the 15 the 30 positrons combined of the two, they're going to be breaking apart. It's PET scans are made by the fact that there's radioactive substances that emit positrons, and those positrons collide. Okay, they put it in your blood and it goes around your body, and then it's emitting these positrons, you've got electrons, a lot of beta electrons in your body. Okay, and when these collide with one of these positrons collides with one of those, say 43 particle mass beta electrons, or 27, there's a rough force there so that they break apart. And when they do, the interior high charge photon of each go in opposite directions because they're highly repelling. And that makes it possible to do imaging, the imaging of PET scans. But anyway, in a collider, when you collide two protons, and you see all these little particles coming out, those are not photons. Photons is a thick soup that's surrounding all that. And they move through those at such high rate that kinetically enough photons are sent out in every direction. I mean, you can either have a massless emanation that's going out in all directions as these move through, like the standard model would tell you to think, or you can say there's a thick soup there. It's also called an ather of these subatomic particles everywhere, and that as these things are broken apart, say something with 15, a mass of 15, moves through there, and it starts colliding with those singles, and those singles are going out in every direction. It's just like a movie, okay? A film. Now we do videos. Everything has, when you're looking at an image, everything has to do with time passing, and you're as okay at one moment in time. This 15 part, let's say 15 mass composite particle is moving through this soup that has mostly visible light photons in it, and at one point it's colliding into a whole bunch of those, and they're going off in all these different directions, making visible light. At the next moment, it's up here, and then it's sending more. And when it does, it's some of them. These are reaching all different locations, and that's how this really works. That's how it would work if everything had mass.